Okay, so the first thing you want to do is draw a drawing. If you notice the trebuchet, or I'm sorry, the catapult is on the ground. All right, then you're going to want to draw the velocity, and the velocity is going to come out like right here. It's going to be it's going to follow your initial velocity is going to follow the direction that your projectile leaves the trebuchet, or leaves the catapult. So something like that. An arrow kind of coming out like that. Now, the angle I know kind of threw a few people off. This is not your angle between the neck of this and your arrow. Your angle, actually, theta, let me show you something. If you look at it, theta is kind of like a zero that has a flat line on it. That flat line, actually, the reason they picked theta is because that flat line means that this is an angle with your horizontal. That's the, lore behind it. So anyway, the thing is that your horizontal is all the way down here, your horizon. But if you will recall from earlier math, geometry, I think this is even earlier, parallel lines kind of act the same, especially with angles. So we can and there's an infinite number of lines parallel with this ground here. So I'm going to just draw a dotted line that is supposed to be parallel with your horizon or your horizontal. So this is parallel to the horizontal. So the angle, if you remember kind of the arm thing we did, that this makes with the horizontal is going to be called theta, just like that. And this, by the way, I'm so sorry, is your initial velocity. V naught. Okay, your overall initial velocity. Think of it that way. So keep that in mind. I just kind of want to set that up and let you know I'm doing that. Now, one of the most important things you're going to do is draw what this thing is actually, where it's going to go and kind of your best guess. This one's pretty shallow. I kind of didn't have my picture of my catapult. Didn't have it really firing the best way. So let's see if this is going to do the right thing. Not perfect, but you see that it kind of goes up and then down. And I did want to point this out. Your highest point is right here. That's like the very top of this. It's not right in the middle of this down here of your, distance that it travels on the ground. So we will probably need to take a look at that. A few things. Let's talk about what you can actually measure. You'll have a protractor, so you can measure theta. Now, you can measure, you're going to have to do some defining of things. You can use the letters I use, you can use your own, just make sure they're indicated in a drawing. Okay, so this right here, the actual height that this gets fired from, right here, we'll call that H1. And you'll see why I'm kind of labeling that H1 in just a minute. It's supposed to be a straight line from where it left in the ground, where it left the catapult in the ground. You'll also be able to measure, I'm just going to kind of draw this like this down here. That's supposed to be a straight line too, but this is just indicating the amount of space. You'll be able to measure this, and I'm going to call this delta x, or change in your horizontal position, and I'm going to actually put that as TOT, which means total. I'll explain that in a minute too. Now you also have your stopwatch on your phone or whatever, and so we're going to put that as time. I'm also going to put this as time total, and again, I'll explain that in a second. So these are things that you're going to be able to measure. Time, your delta x overall here, your height that it left this, and your and theta. So that is super important to know. Now, let's look at this. This is going to be the kind of problem that you're going to want to break up into pieces. That also is super important. So let's do this. Let's do the first part. I'll do this in blue. Okay, so the first part, you're going to want to see it when this gets to its highest point. That's because your vertical, your up and down velocity at the highest point, I'll put Vy, just that's the highest point. Put that wrote. Highest. There. Highest point is V sub y is what I'm calling it. And when this gets to the very top, it's just like you threw something straight up in the air. I guess I should do this. Your acceleration due to gravity, because gravitational force is the only force acting on it, no air resistance. So your acceleration due to gravity is pulling it down towards the Earth. And this initially has a little bit of upward velocity, and it goes up, 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 till it slows. Well, actually, till it stops, and then it changes directions, and it starts to speed up until it hits the ground. And so at the very highest point, this is 0. Now what we're going to, oh sorry, my dog is barking. What we're going to do is we're actually going to divide this up into 2 separate problems. I'm going to kind of draw a line right here. maybe. Okay, so we're going to just look at this part first, just up here, and then this line. We're going to kind of ignore this H1 here. We're just going to focus on this. So imagine, like, you know how movies have a sequel, like a ball like gets launched up into the air and it stops, and then and then just freeze frame and just they leave it literally hanging in the air. And then for the sequel or whatever, the first shot you see is that like suspended in the air ball, and then they hit the play button or whatever and it falls. That's kind of like how you need to imagine this. So anyway, so we're just going to be looking at this section to start off with, and then the second part we'll look at this section, and then we might have to jump in and out of looking at the overall stuff we can measure here and there. So first of all, let's do this. You know, at this point, at the highest point, so we're just looking at, let's see if I get this. We're just looking at like this section right now. Okay, yeah, that didn't make the best circle, but yeah, just this top section right here. All right, so I'll do this in blue. Hang on. Okay, so let's look. Now, since we're kind of looking at it from this point, this is different from your height over here. So I'm going to actually label this height 2. I'll talk about why I do that in a minute also. And I also want to break up your initial velocity because this is not in the x direction, this is not in the y direction, it's in both. There's got like a piece of it. There's a certain amount of this. It gets broken up into your over and your up. See, so you got a piece that's going over. That's going to be like your velocity in your x direction, which doesn't change. It's constant because there's no acceleration. Then you're going to have your velocity in your y direction. That's the over part of this. All right, or I'm sorry, the up part. So let's look at this. You know that both of these, this is so important. I've been seeing people forget this a lot lately. You need to write V naught next to both of these because they're both pieces of this overall vector, this overall kind of slanted angle resultant vector. These are the components or the pieces. So if you remember the memory trick, this one's cosine to your angle, cosine theta, and this one's on the other side. So this one is sine theta. And you're going to actually measure. Remember, you're going to get a number. Don't worry about what you're going to kind of put together. You're going to get a number for this theta. And then if you multiply it by times sine and cosine, then you are going to, it's going to be, this thing together, this cosine theta and sine theta are going to be actual numbers that you can use. But spreadsheets do that better because they get, like, the numbers get weird. Talk about that in a little bit. Okay, so this is our only acceleration, this acceleration due to gravity right here. So there's no acceleration in your x direction at all. So this v naught cosine theta, the only way to change velocity is to accelerate it, like same direction or opposite direction. That's the only way to change it. And we're not doing that. So your velocity in your x direction up here is still just v naught cosine theta. Okay, so we have that. And this, how far it travels between here and when it hits its highest point, how far, like in the x direction, let's call that delta x1. Oh yeah, and the time it takes for this, it's not going to, and notice this is not halfway, so it's not going to be just half the displacement and half of the, half the time. It's going to be a little bit less. And I just noticed this down here on your total x, that probably needs to go here, but I'll talk about that in a second. Anyway, so let's, I'm going to go do this over here. Let's do the blue. I'll do x and y, the different pieces of this. All right, so your acceleration in the y direction is going to be due to gravity, and we know that that's -10. I'm not too worried about numbers right now, but that will be -10 because we are on Earth. Unless anyone had plans to take their catapult to space, which I probably need a field trip or something. Anyway, so, and notice no acceleration over here. No need for that. Let's see. Then we have your velocity initial and your velocity final, because the gravity, the gravitational force is pulling this down. It's accelerating this object, so you have both of those. No acceleration over here, which means that your velocity is not going to change. So we just call your velocity on this side just v sub x, just because it's velocity in the x direction. I'm going to put this as delta x, if you look back over here, delta x1. All right, and then over here, I'm going to call this, because we're just looking at how high above what it was originally fired out of the catapult at. I'm going to call this height 2, because remember height 1 was how high the projectile actually was launched from the catapult. All right, so if you set your picture up, this should be pretty easy. Okay, so let's look. V sub x, well, that is your V naught cosine theta. Okay, x, we don't know that. That's going to be, you could kind of measure that with a camera or something, but it's really hard. The same thing with time, and the same thing with how high up above where you shot it. This is definitely hard. So let's look at this. If we look, since we're just looking at this one piece, right here at your highest point, what is your final velocity in your y direction? Because it's final, this can be either final or initial depending on which way we're looking at it. If we're looking at it from like the first part of the movie I talked about, or the second part, like, you know, the movie that has the sequel. So right now, this is where it ends. This is where they kind of suspend the ball in midair if you're thinking about the movie thing, or it's, you know, stops before it changes directions. So your final velocity up there is 0. Now your initial velocity going up and down in your y direction is going to be v naught sine theta, because that's just that one piece of this. Okay, so we've got that. And this is all we have. Now look, this is good. It kind of looks like right now we have 1, 2, 3 pieces of this puzzle. Let me write the kinematic equations. Oops. Let's go. Velocity final equals velocity initial plus acceleration times time. Velocity final squared equals velocity initial squared plus 2 times acceleration times displacement, which that could be delta y or h. We probably will call that h in just a second. That's final. Anyway, then you got x final equals x initial plus velocity initial times time plus 1/2 a t squared. Okay, let's see if that does that. Velocity would be like that. That's supposed to be velocity right there. That's a v. Okay, which I'm sure you all know that. All right, so yeah, we should be able to, because you got to find time, you got to find all this stuff. You got to find time, you got to find your delta x, you got to find your height. So let's say start off with time, and let's look at this. You can find your time with this one, because let's see, I'm going to rewrite it real quick. You got velocity final equals velocity initial plus acceleration times time. Okay. Come on, it's like kind of got some lag. Okay, no velocity final, that's 0. So, and oh yeah, this is actually, I'm going to do this as negative g. I'm going to put the negative up here because we know it's going to be going down. You'll see why in just a second. So that's going to be like negative g. That's supposed to just be 1 negative sign. There. Okay, so this would be, I would just subtract vi, and that would give me velocity initial equals, I guess I can go ahead and move that, and then the negatives also cancel out. I'll put that as negative g, and that would go over to this side. But anyway, that would give you velocity initial over acceleration due to gravity equals time. And hey, we know this is velocity initial. It is v naught sine theta over g over time. Okay, this is looking really promising. This, maybe you figured it out, but let's look. Okay, so this is a given. Your g is a given. Theta you can measure. Now here's the only problem. This v naught right here. You don't have that. But don't worry, it's easier to find than what you think. I'll talk about that in the next video. Just remember, velocity is constant the whole way. That might make things and think about what you can measure. The total way, it's constant.